surface curvatures. It's not a class in surface curvature. It's not a differential geometry class. It's a tale of what I went through with Maple to figure out something that I should have known because I did take some differential geometry years ago, 50 years ago, when I did my thesis in relativistic cosmology. And I got dragged into this by a question that I received from a participant in one of my webinars who asked something about a textbook that's on the market, John Oprea's differential geometry book, which has errors and some lousy Maple in it. And I realized I didn't know enough to answer the question. So this is the story of what I went through to make sense out of what I should have known about surface curvature. So I begin with some of the things that we need to have in front of us. Curvature vector. So you have a space curve, you define a curvature vector. Try to use consistent notation. I call it the Frenet curvature because there's all different kind of curvatures that's going to show up today. So the curvature vector is essentially the principal normal, which is a unit vector, multiplied by its length. Now, there is this thing called a normal section for a surface. And this is the thing that I struggled with the most, trying to visualize what they were talking about. What they're saying is you have a surface, there's a surface, you have a point and a normal sticking out at that point. You draw normals through that normal planes that contain that normal. It cuts the surface and forms a curve. You look at all such curves through that point, and then you will compute the curvatures of all those curves. It's a Frenet curvature of all those curves. Those are called normal curvature. The maximum and minimum, depending on where that plane is, principal curvatures. So those are typically called K1 and K2. The average is the mean curvature. The product is the Gauss curvature. I didn't know what any of this stuff was. Turns out the Gauss curvature is intrinsic to the surface, mean curvature is not. So what did I have to do to get some images in my head to make sense out of this stuff? So here's the game plan. Needed a surface. Now all the surfaces in the textbooks, they're nice. They're spheres and cylinders. There's not enough wrinkles in them for things to show up. And if you make it too bad, you can't do any computations. So I picked this one. And the point 115 has integer coordinates, is on that surface. And I want to put a normal vector there at that point. I'm going to get a tangent plane. I'm going to get a family of tangent vectors in the tangent plane so that I can use those as guidelines where I'm going to put these normal cutting planes. And I have to do the intersection of these cutting planes with the surface, and that turned out to be a real bear. Then I got to compute the Frenet curvature of each of those curves. Then get the extreme values. And then I compare what I got with values of the principal curvatures that you can look up. There's formulas for that. And then on into these other kinds of curvatures and so forth. So here's the Maple worksheet that I used. I need plots because I'm drawing pictures. And I work primarily with student multivariate calculus because there's a dot product and a cross product in here, and it's simple, and it works over the reals, and you don't get all conflicted with some of the properties of dot product and cross product in, let's say, linear algebra or even vector calculus. But I needed vector calculus and I needed linear algebra for other things, and they have commands in common and they conflict. So what I did was I aliased a little short name, VC for vector calculus and LA for linear algebra. And then when I needed a command from one of those packages, I went VC : got the command. And then the surface Z equals, I use an uppercase Z. So now I have to do some computations. So,
real quick, could you have done any aliases before you loaded the packages and then just loaded VC and LA?
could I have done, say that slow.
Scroll back up. Scroll back
Yeah,
up.
yeah, I know what you're saying.
Could you have done the alias before you loaded the packages?
You
You only loaded the student multivariate.
oh yeah, that doesn't make any difference with order.
And then use the alias in the with command. That'd work as well, wouldn't it? If you're done with. Oh, no, I'm sorry. You haven't loaded those packages at all.
Correct. That's what I'm avoiding, right? I only want the one package loaded. I don't want the other packages loaded because then I have to sort out which command, and you got to put a colon dash, and it gets really complicated. Okay, so I need some quantities here. The surface I define parametrically as a position vector, x, y, z of x and y. Then I need tangent vectors, so that those are derivatives. I'll use the mouse. Those are derivatives, derivatives vector x and vector y. And I use rx and ry for names. But because I had assigned to capital R, I can't subscript R with an X because that's a no-no. If you assign to something, you don't, okay? You have to make it an atomic, and making things atomic is a pain in the butt, so I just use a different letter. Cross product gives me a normal, and then I normalize that, and again, I use a different name. And here are the vectors. This is what they look like. So you have your here, surface, Rx, Ry, normal, and the unit normal. Then I have to work at a point P, because you don't want to be dragging all those X's and Y's around all the time. So I subscripted with an extra letter P, because I was working out a point, when I evaluated at 1, 1. Okay, so again, different names, so there's no conflicts. And this is what those vectors look like. You can see here, this is the normal, 461, and this is 461 divided by 1 over the square, or multiplied by 1 over the square root of 53, but Maple rationalizes immediately. Okay, now I need a family of tangent vectors. So I tried different things, and I ended up with this family. You have the two basis vectors, two tangent vectors, Rx and Ry. And I just took a linear combination. I tried A times 1 plus B times the other. But now you have a 2-parameter family, and then, so I tried, let's try a 1-parameter family, cos and sine. So there's a family of tangent vectors through that point. Is this good enough? So I made it visual. Okay, the red vector is the normal, and the black vector are my tangent vectors. And they appear to be sweeping out the tangent plane. So I said, okay. And you'll notice how I did it. I used the plot vector command in the vector calculus package. And I've written several times in Maple primes, when people have asked about plotting vectors, you get answers back that say arrow. Well, there are 2 arrow commands in Maple, one in the plots package and one in the plot tools package, and they have different syntax, and they're difficult to deal with because they don't remember where the tail is. But you can do that in the vector calculus package. So the plot vector command will plot a whole bunch of different kind of vectors. So I use the plot vector command. And I normalized t so that I didn't have a scaling problem. And then what I do is I graph it simply, and then you start adding properties like color and width and put labels on and the right orientation so that it looks nice. Okay. Now, in the multivariate calculus package, there are commands for generating lines and plane objects. And that's what this command right here, plane. It's in multivariate calculus package. It gives me the plane through the point, so that's 115 is the point, that contains the two directions, the tangent vector in the plane and the normal vector sticking out. So that's going to be a cutting plane. And then to get the equation of that, you query the thing and you say, give me the representation. So you get an expression, okay? It has x, y, and z in it. And I solved it so I would be able to say z equals. And this is what it looks like. Here's a picture. Okay? The green, does that show up green? Yeah, the deep green is the tangent plane. And the lighter yellow thing here, that's one of the cutting planes. So this blue thing here is a normal. These two vectors down here, you see, it shows up red because of the transparency. Okay, black and red, that's Rx and Ry. Okay? So I looked at this and I said, I think I'm on the right track. I drew this picture. I wanted to see the surface. So you have the surface, you have the, wake up here, you have normal planes. You see I've drawn the normal direction as a line. That's this green line here. This red is the normal section. That's the curve on the surface that I got to get my hands on. And I seem to have this nice family of cutting planes. And again, you can see the use of the explore. And here, the space curve command from vector calculus. Again, space curve command is, I think, one of the better commands. There is a space curve command in the plots package with all lowercase letters, but it's only for 3D. If you have a 2D curve, you have to use the plot command to draw that. This space command, space curve command, accepts 2D or 3D. Same syntax. It's a superior command, so I tend to use it. And then I'm using intersect plot. In order to get this intersection, this red stuff here, I'm using intersect plot. And right across the hall is somebody going to be talking about improvements to intersect plot. And this intersect plot is a little bit on the slow side, okay? So if I wasn't here, I'd be over there listening to what they had to say about intersect plot. So I seem to be on the way to getting these normal sections. Now I need to get the Frenet curvature of those normal sections. So I need to do the intersection analytically. So this is the surface, right? Z equals z of x and y. And this is the cutting plane. I have to intersect those, solve them simultaneously, and there are two solutions. So that gives me two possible curves to explore. And I call them C1 and C2. Which one? Well, I took a shot in the dark. I'm looking at z equals 5, and I just took one of the values of the parameter, and it seems that C1 passes through the point P, so I'm going to use C1. So another visual. This visual, I did not use constrained scaling on the surface, so it looks round. But I'm looking at the normal sections. You see the red dot? That's the point P, and you can see this green normal section. So it looks like my calculation has given me a curve C1, a family of curves C1 that fits the bill. But now I turn it over here. I do this again, and I'm looking. And I'm seeing, so I colored in brown, or whatever that color is, this guy in the back, right? This is the other one. This is C2, actually. And you got to watch this very, very carefully. Watch it very carefully. Watch it very carefully. Oh, right there, right there. You see what's happening right there? Right there. Oh, I can't hold my hand steady. Right there. Oh. Get the message, right? There's a little gap where C2 is the curve and not C1, and this drove me nuts. You know, you look at the visual and and let me show you the effect in the computation of that little glitch. Okay. So, I'm plowing ahead, right? I'm going to use the curvature command in the vector calculus package to get the Frenet curvature of these plane sections, of these normal sections. And it seemed that it was taking forever. Every time I asked for the curvature, I was sitting there, so I timed it. It takes 2 minutes, right? It's not all that bad, but when you're waiting over and over again, it seemed forever. And so I graph the negative of that curvature that I've just computed. And I get these graphs. And I got to explain this minus sign, and I will eventually. Here's a maximum. And down here somewhere there's a minimum. And it's funny looking down in here. And if I expand, zoom in on that, it looks like this. And here's that gap. And I beat my head against the wall countless times trying to figure this out, okay? But I was encouraged. I was understanding what they were talking about in the textbooks I was reading. Get the normal sections, get Frenet curvature, max min, and you're going to get the principal normals, principal curvatures. Okay, so I computed the principal curvatures. Now, it doesn't look, it's not laid out nicely because I had to expand. Maybe if I made this table bigger. Can I make this table bigger? I could drag it, yeah, but then that only drags one side. Yeah, that's better. Yeah, we're good. We're good. Okay, so I did a numeric optimization. The maximum, that's the one up top, that's this guy. Minimum, I get this number. These are exact, and there's some formulas that blah, blah, blah. We'll get to that. These are exact, and I float those. This number and that number match super duper. This one, I think you get a match to about here, 07, right? You see 607? It matches to about here, okay? So that glitch has a small effect on my understanding. I can almost convince myself to ignore it. I'm on the right track. I figured out what they were trying to tell me. Let's keep going. Principal normal. Let's look at this curvature vector principal normal thing. So there is a principal normal command in the vector calculus package, and if you put in the option normalized, it comes out to be a unit vector, and I'm only looking at the point of contact, and I would like to know the angle between the principal normal and the normal to the surface. And I did it graphically, except for a couple of little glitchy thingies here, which I was expecting. The angle seems to be pi. In other words, the principal normal on these normal sections is directly opposite the normal to the surface. And that's the reason for the minus sign. That's where that minus sign is coming from. They're taking into account that difference. And so, minus sign. You have a question? No.
No, I'm just.
Okay. All right. Okay. All right. Well, after you spend enough time in the classroom, you learn to look at students' faces, and what you look at is for the wrinkles right here. As soon as you see that, you know you got a problem.
The headache look.
But with these glasses, I can only see the screen, right? I wore eyeglasses. I was nearsighted for like 65 years, and just recently had cataract surgery. So now I can see through that wall. I've got X-ray vision, right? But I can't read a damn thing. Right? So this is for reading, and once I put these on, I can't see anything out there. You don't exist out there. Okay, so at this point, I said, I understand this stuff, but I got to keep going. I've got to look at this more closely, but I think I understand what they're trying to tell me. So you go to the internet. You used to go to the stacks, and now you go to the internet, and you find all kinds of things. And one of the things is this formula for normal curvature. If you have a curve, now that's a second derivative, and you got to ask yourself, what are they differentiating with respect to? Is it arc length, or is it the natural parameter that you have? Because you never have arc length as a parameter, okay? Well, because you have this factor in the denominator, then you can differentiate with respect to the parameter that you have. It doesn't have to be the arc length. So let's try that. Let's apply that to C1. And you can see the use of 2D notation, which I think is easier to read than diff this, diff that, norm this. Okay, so there's your second derivative, dotted with the normal, norm brackets, norm squared. It's a mess. It's this much stuff. It's full of complex sign of and all that kind of junk. So I started looking for ways to simplify, and I simplify, and I get this expression. I say, look, that's nice. Look how nice and neat that is compared to the big stuff. So I graphed that. Lo and behold, it's the shape that I was looking at, but no glitches. Oh man, I was really, this was a, so you calculate this point, and you calculate that point, you see if you got the two principal curvatures. And in fact, you can do it exactly. Here's Maple's maximize and minimize commands. You get roots in the denominator, so you rationalize, but now you have products, so you have to expand to take care of the products, and then you have to simplify to put everything back together. And those are the two expressions that I use when I said you look them up in some place and you find principal curvatures. And if you've got the principal curvatures, then you can take the average and get the mean curvature and take the product and you get the Gauss curvature. Man, I was just feeling just Jim Dandy at this point. And I said, wait a minute. I worked really hard to get these normal sections. And I had different curve families that I had been experimenting with. And I realized this particular family is not a family of normal sections. I devised this one, and you can see what I did. Okay? I just lifted a circle up. I said I'll go around, but those are not normal sections. Let's get the curvature of that family. Lo and behold, it is not as monstrous as the curvature of the family of normal sections. Got the principal normal for that family. That doesn't look too good. Okay? And the reason why it's extra ugly is it's a unit vector, and you can see the same factor in every one of these. It would be nice if Maple had a nice simple way of factoring out from a vector. A simple way. Just go, factor out of the vector. Take this out. Okay, but it's not too bad. So that means I can write the curvature vector, because I've got the curvature and the principal normal for that family. So there is the curvature vector. Now, the component of the curvature vector on the normal is supposed to be the curvature, the normal curvature. Let's see if that's true. Let's take this dot product and see what we get. Does that look familiar? Does that expression look familiar? So you compare it to what we had a few minutes before. It's the same thing. Now you think, that's it? Oh. Everything I'm reading has got this guy's result. I don't know how to pronounce that, because I don't know what language that is. Is he French? Is he German? I don't know. So I'm not going to pronounce it. M's formula. What is that formula? It says the normal curvature is the curvature of the family, whatever family you have, times the cosine of the angle between. That's this dot product stuff we just did. Let's see if it works. So there's the curvature vector. Now what is the curvature vector? K times, this is the principal normal. You dot it with n. Okay, but this dotted with that, they're two unit vectors, so what's left is the cosine of the angle between. Self-evident. And of course, you have to do the computation to really feel satisfied. So I get the angle between the principal normal and the normal to the surface. This is for the family that's not normal sections. Okay, the angle command is the one from multivariate calculus. It's not quite so entangled as some of the other. There's one in linear algebra and there's one in, no, the one in linear algebra is called vector angle. And there's an angle command in vector calculus. Okay, so I have this expression. Let's multiply K times cosine of that angle. Well, that's almost familiar, but the other ones had a leading minus sign over here, but that was a plus 20, so the minus sign is inside, and if you simplify the difference, you get 0. Now, this Musner guy is used, I don't know how to pronounce that. His result is used to claim that it didn't make any difference what the tangent vector, what curve you took, it's the tangent direction that matters, okay? And that's built into a lot of this computation. Well, now let's jog over, step over. Because the next stuff that you start reading, they talk about fundamental forms. All right, so here's fundamental form stuff. Remember, we have a position vector, description of the surface, and it looked like that. And we took first derivatives, and now we need to take second derivatives. So we have an Rxx, Rxy, Rry, second derivatives, and these are what the vectors look like. Because these are just quadratic, so these come out to be constant, made my life a whole lot simpler. And then you have the fundamental forms. The first fundamental form I was familiar with because I'm a differential geometer way back 50 years ago. Metric tensor, that's the metric tensor. And it's the dot products of the tangent vectors, first derivatives, okay? And if you write it as a quadratic form, then you're getting arc length. For the second fundamental form, you take these second derivatives and you dot it with the normal vector, and you get a different different quadratic form. It's called the second fundamental form. Okay, I could do that. Let's see what happens. The numbers turn out to be these. Okay, 17, 24, 37, and minus 4 and minus 6, 1 over the square root of 53. And here you have the four numbers arrayed in a matrix 2 by 2 matrix. And here you have these 4 numbers arrayed in a 2 by 2 matrix. And then you come across this formula that says the normal curvature is this quadratic form divided by that quadratic form. And if this thing is a unit vector in the surface norm, then you only got to look at the top. A whole new avenue of exploration to look at. But it's not black magic. Okay? I'm going to actually drag you through some calculus. We need to distinguish between 2 different kinds of differentiation. With respect to t, the parameter that you've got, and with respect to s, which is arc length. The curvature vector is the second derivative with respect to arc length. Done. But you never have arc length, so you've got to do a lot of other stuff. So this is k principal normal. And if you do the derivatives, second derivative here, right? So you're going to have second derivatives. And then you're going to have first derivative on r, but second derivative on the argument. And so when you differentiate here, you get, for each derivative, you get one of these x dots coming out. So you have a square here and an x dot, y dot squared. Okay? Then we dot that with n. So we know what's going to happen on this side. It's going to end up as kn. I keep the first 3 terms together, and I look at these 2 terms. N is the surface normal. This is in the tangent plane. Rx is in the tangent. This is in the tangent plane. They're orthogonal. You get 0. Oh, got to make this box bigger. Got to make this box bigger. Oh, does that fit? Yeah, that's good. Okay. Well, not quite. Got to make this side bigger. You know, see, the thing is, you can't line up equal signs in Maple. Multi equations can't line up equal signs. So I make a two column table. Left side goes in this column. Right side goes in that column. That's why I had to expand everything. All right, we got it here. Okay. N dot this guy. You see, that's the E. N dot this guy. That's the F. And the G. Okay, that's where the second fundamental form is coming from. Okay, it arose naturally as we looked at this R double dot, the curvature vector. Now, that's a dot, so that's differentiation with respect to arc length, S. But you have to use the chain rule, dx dt, dt ds. And so that's happening everywhere. You can factor that out. So factor out dt ds. Put it in the denominator, becomes the SDT. This is what that formula said. So it's not black magic. It just came out very, very naturally if you just follow out the differentiations. And if you look at the denominator, the ds dt squared, I got to do the same thing here. It's not going to fit. It's not going to fit. Okay, here's what I'm going to do instead. Okay, I'll magnify it until it blows up, right? All right. Okay, I'll leave it like that just for this thing. Okay, so what is the SDT? It's the norm of the first derivative squared. So you're taking a dot product between these two vectors. So there's your Rx dot Rx, there's the Rx dot Ry and Ry dot Ry. So those are the coefficients of the first fundamental form, right? So it's not black magic. And of course, I wasn't happy until I applied this to the example that I've been working on. So there is my curve. You need a tangent vector. Okay, so you differentiate this curve with respect to the parameter. This is the parameter along the curve. And then right at the point, P equals 0. So there's the tangent vector. But I got to express that tangent vector in terms of the tangent plane coordinates. Tangent plane has two vectors, Rx and Ry, I can use as basis vectors, which define the coordinate system. And how will I express one in terms of the other? Well, take a linear combination and set it equal to this vector. And that's what the equate command does. It equates components. Solve for those two unknown coefficients, A and B. Now, it comes out that they're cosine sine, which you couldn't guess from just looking at this thing right here. So the vector that I want to look at when I do this second fundamental form or the first fundamental form is this vector, because those are 2 by 2 matrices. And it has to be a two vector, not a 3 vector. So you do that. Linear algebra has a bilinear form command. Use it twice. 2 here, 1 here. Lo and behold, normal curvature. So it did work. Another jog to a different direction. The more modern books, they talk about the directional derivative, the shape operator. Okay, now look at this definition. Is that big enough? I could probably try that bigger. What they're talking about here is, on the surface, you have unit normal. This symbol is supposed to be the negative of the directional derivative of the normal in the direction of a tangent vector. Where does it point? What does it look like? Okay? Then the theory goes on to say that vector, this thing, is in the tangent plane. Is it really? Okay, so it's in the tangent plane. That means you have a mapping from the tangent vector t to this other vector, which is in the tangent plane. So it's a mapping of the tangent plane to the tangent plane. Oh, the headaches. Okay? And this is called the shape operator. In some books, you start out talking about, here's the shape operator. Here it is, kid. Shape operator. Oh, man. One of the formulas that shows up is that's the shape operator, and it's the product of the two fundamental forms. One of it has an inverse on it. Oh, what does this look like? So you carry it out. You see what's happening, right? You use Maple to see what's happening. And it's a 2 by 2 matrix. And I would like to share this aside with you. And I hope it works. I was stumped for a long time because every time I thought of a tangent vector, it had 3 components. That's the only way I could compute it. You got the R, you differentiate it, it's going to have 3 components. The shape operator is a 2 by 2 matrix. How can you be then incompatible? So you go to the internet and you rummage on the internet, and I hope this comes up. Yes, there's a physics forum that I spotted, and somebody's asking exactly the same question. If you look carefully, they're asking that question. Shape operator is 2 by 2. Tangent vectors are not 2 by 2. What the hell is going on? And this goes on and on and on and on, and nobody ever answers the question. You don't have time to read all that. Nobody answered the question. Nobody said flatly what the hell is going on. And the answer, we have seen the answer. We did it. You have to express the tangent vector, which has 3 components, as a vector whose coordinates are the tangent plane coordinates. It's as simple as that. But no book that I read ever said that in plain English. So anyways, that's an aside. So I want to do this directional derivative stuff. Vector calculus has a directional derivative command that will deal with the directional derivative of a vector. There is a directional derivative command in multivariate calculus, but it'll only work on a scalar. There's also one in physics package, but that one normalizes the direction vector, and that's not what I want. So this is the only one that works right. But everything has to be a vector field. So you've got to convert everything to a vector field. Now, I like to use this command, basis format false, so that vectors are displayed as column vectors. Otherwise, you're going to get a sum across the basis vectors, and I just find that harder to read. So I make the vectors that I need into vector fields, but I use a different name. So that's why it's rho x, rho y. And I think I used new, but I used new before, but anyway, I overwrote it. So new. And then for tangent vector, I take a linear combination of rho x and rho y. And if you want to see what the vectors look like, they look like that. They look like they did before, but only now the data structure is vector field. Apply the directional derivative command to the normal in that direction. You get a vector. I call it M1. You do it in this direction. I call it M2. And I'm only interested in what happens at the point P. So I put x equals 1, y equals 1. These are the vectors. They are 3-component vectors. So to make this thing work now, we're going to have to express those in terms of the tangent plane coordinates. So here's how you do that. We've already done that. You have a solve and an equate, and you get a solution. And then AB, I evaluate, and I get a vector, M1 and M2. Those are 2-component vectors, and that's what they look like. And if you could see it on the screen at the same time, you'd see all I really did was lop off this bottom coordinate. And at first, I'm thinking projection and blah, 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 blah. The answer is what I just did down here. This made more sense to me than anything. Okay, so there we go. So then I said to myself, okay, I know what I want to map. I got 2 basis vectors, Rx and Ry. I want to map that to what I got when I did the directional derivative. I want to map this to what I got when I did directional derivative. And it only takes 2 vectors to define the matrix for the transformation. So I ought to be able to write down what the matrix is. Now, these are bases, the rho x and rho y, they're basis vectors. They behave like 0, 1, 0, 0, 1. In spite of the fact that they're not orthogonal. So all I need to do is take these 2 vectors and make them the columns of the matrix. And I do that. And I say, is that W? Is that this shape operator? Yes! It's the shape operator. I'm learning something. Okay, and are these guys really in the tangent plane? Well, I didn't do a proof of it. I just said, okay, I'm going to look at these 2 guys. I'm going to take the dot product, get 0, take the dot product, get 0. They're in the tangent plane. Are there any consequences? Yeah, a couple of consequences to this. And again, I checked it, and I didn't include all of the theory here. The eigenvalues of that W matrix are the principal curvatures. So half the trace is the mean curvature, and the determinant is the Gauss curvature. And there's a whole lot of stuff that's written about that. And so I did it, and it works, and it all checks out. Now there's another thing that shows up here called the Gauss map. The Gauss map says treat the coordinates or the components of that unit normal. Okay, you have three chunks. Treat that as the parametric representation of a surface. So you are mapping that normal vector to a surface. What does that look like? There you go. The sphere. And that's what they tell you it's supposed to look like. But it has these funny lines on it. What are those lines? So I said, okay, let's explore the lines. So let's draw some space curves. Let's fix y, but control it by a slider, and graph it with respect to x. And so I got this guy, and it's showing me the curves. Come on. Showing me the curves that I saw on that hemisphere. Then I got a little fancy. I said, let's make loops. Let's take loops in the plane and let's raise them up and see what happens. So I did that. Because I'm trying to find out, what does this Gauss map tell me? I don't know what this Gauss map tells me. Okay, so there's the Gauss map. This is what happens when you lift that, where you take the images of that. So I don't know what the Gauss map tells me. So the last thing I want to tell you about, right? The last thing I want to tell you about is geodesic curvature. I told you there's a million kind of curvatures. So I'm going to talk about geodesic curvature. There's two ways to talk about two definitions. And here are the two definitions. So look at the first one. You have a curve C in the surface. Project that to the normal plane, to the tangent plane. So curve of the surface, project it to the normal plane. Okay? Get the Frenet curvature of that curve in the tangent plane. That's called a geodesic curvature. That's one description. Another description. Get your curvature vector for that curve in the surface and project it onto this vector, i.e. zeta. Project it onto this vector, n cross t. So n is the normal, t is a tangent vector, a cross product is going to be back in the tangent plane. So this is in the tangent plane. Project the curvature vector onto this vector in the tangent plane. The component is the geodesic curvature. Well, 2 is easier to explain or visualize than 1. And that number 2 guy, you can express as a formula, because here's the n cross t, there's the curvature vector. It's a triple scalar product, k dot n cross t. This is a triple scalar product. This is a triple scalar product. And the reason why you have this scale factor down here is because these derivatives are with respect to the parameter that you have, and it's not with respect to arc length. So that's easy enough to calculate. So I did that, and I put approach 2 first because that's easier. So I'm just looking at the point P. There's the curvature vector. This is the curve C, which was the family that was not normal sections. You need the tangent to that, so that's the first derivative. And then if you take the k dot n cross t, this is what you get. And this is supposedly this geodesic curvature. So now let's see if that checks out by doing this approach number 1. But approach number 1 stumped me for a while because I didn't know how to project this curve up onto the tangent plane. I tried projection matrix from linear algebra. There's a projection operator command in multivariate calculus, and I wasn't getting anywhere. So I just stopped and said, what am I trying to do? How do you project a point to the plane? It's a short Shortest distance. Simple as that. So here's your tangent plane. This is the representation of the curve. This is, remember, now we're just calculating this for one member of the family. This is the expression for the tangent plane. See, there's a tangent plane command in a vector calculus package. So what is the distance between them? Well, subtract norm squared. So that distance is a function of x and y and the parameter p. Normal equations, right? Differentiate d with respect to x, d with respect to y. Solve for x and y as functions of p. Put that back into this guy, which is the curve in the plane. That's what it looks like. And if you notice, it goes through the point 1, 1, 5 when p equals 0. So I drew a picture. Did I do this projection stuff correctly? Okay, you can see the piece of the plane. That's the tangent plane, okay? The black curve is the curve in the surface. The red curve is its projection onto the tangent plane. Can you see that it lies in the tangent plane? Okay, so it's the projection. So I looked at that and I said, did it. Okay, so you take the curvature of that curve, evaluate it at the point of contact, and you get the same number. And I said, I got enough here for a 1-hour webinar or a presentation here at the conference. Any questions? Yeah.
So, it sounds like one of your big pitches, I'll use P, is to maybe standardize these packages, so that there isn't, I mean, is there any good reason why block vector exists? I mean,
Look, I'm not even going to go there because I fought that battle and I lost. And it's never going to change because of the way Maple gets developed. This little chunk over here, this little chunk over there. There's no guy like a Wolfram standing like a cop over the development process. So it's all, you know, it's all over, okay? And it is what it is, okay? So I'm not even going to go there. I mean, I'd love to see it all straightened out, but it ain't going to happen.
So when is Maple going to learn how to typeset stuff that's in italics? Look at that, evaluated at p equals 0. That's nonsense. Look how close it is. Look how close that p is to that line. It's nonsense.
This thing right here.
The same thing happens with x squared.
Yeah.
It shoves stuff over, and it looks like hell.
I agree with you. Right? Let's see. Now Daniel's not here.
But it's only when there's italics. When it's this font is not italics.
Well, there's other stuff in here. There was one place where in the denominator I had a norm squared. The norm bars on the left are longer than the norm bars on the right, and the square is way over displaced. There's lots of stuff like that.
I found a way to fix that once, but I can't remember how it went.
There's another one that drives me crazy. If you subscript a variable with as a table entry, like x sub 1, table entry, not an atomic, okay? And you want to put a prime on that because you want to differentiate it. Well, either your prime is here and your 1 is here, or it's like that.
So I took you off topic by going through the
Yes.
display and the system, but back on content, because we all agreed that we don't want to worry about the algebra and we can't even worry about the content, the concepts, right? I mean, so I mean, realistically, I mean, honestly, I avoid a lot of the curvature type stuff in class because it's just, the students have no conceptual feeling for it, and to try to spend enough time for them to build that conceptual understanding, I don't have time to do that. And it's not worth it to spend a day to further confuse them. So how are we gonna get past that? How is this gonna work its way into more common practice, more standard?
I think the answer to your question is that anything you want to teach, you can do a better job using Maple than you're going to do with a pencil and paper. If you want to teach curvature of a plane curve, all right, this is surface, this is much more harder. You want to teach curvature of a plane curve, you can actually do the computations, which is how is this thing turning. For a plane curve, it's even easier because you could actually look at differentiate the angle. So anything you want to do, in my opinion, in the classroom, you can do a better job if you do it correctly, wisely with Maple than with a pencil and paper. And the second half of my career, from 1986 onwards, when I put in a grant for Maple in the classroom, blah, 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 and then started with Maple in the classroom. All the conferences I went to, everything I wrote, the message was the same. You do a better job with Maple than with a pencil and paper. Change the curriculum. Admit the fact that pencil and paper is passé. Use Maple or a tool like Maple to get at the concepts before you worry about drilling in skills. Okay? And I think you can do it for any subject if you think about a wise use of the tool.
But you can't do that because the professors like myself who are teaching these
That's right.
classes,
So my answer to that is, I phone up, I make one phone call to Brooklyn, and we take care of you. Okay? No, it's never going to change. I admit it, Mike. It's never going to change, which is why I retired from Rose-Hulman, because I realized it was never going to change.